Thank you, everybody, for attending today. Jim Vaughn will be presenting, and ISPC is a non-for-profit organization, so um, we will have a donation button in our chat today, and obviously, if you can donate, please do. That's how we can support these free webinars, and if you do donate, we will give you a certificate and send that to you in the mail, so you can claim that on your taxes. So without further ado, I will have Jim take over. Thank you very much.
Okay, good. Thank you, everyone, and welcome. I'm going to talk fast, so you're going to have to listen fast. This is when we normally do this presentation for our clients, it's about 4 hours, and if we go out and do practical online, that makes it for a whole day. So I'm going to try to cram most of this information in, and hopefully the things that you need most, not the things that you've heard all the time. Now, hopefully, we have people out there seeing. I can't look into a room and see everybody sitting there, so I'm assuming that you're all there. At the bottom of your screen, you should have a raise hand. So if you have a question that you want to ask, if you click on that, Ryan is monitoring this page and he can see that. So let's move ahead and get into our topic. So the first thing is that we have three ways that we can do work. Now, we can insulate, we can isolate, or we can work it as if it's dead and grounded. Now, with isolation, it's a little bit different than insulation. For instance, these guys over here on the left-hand side, they are insulating, and they're going to be putting cover up on the circuit to insulate conductors. They're wearing rubber goods, which also provides insulation, and their primary means of protection is their rubber goods. Now, we're not going to spend a lot of time talking about it, but the bucket that they're working out of for gloving is known as a Category B bucket, and even though it is isolated by an insulating boom that we test for integrity, the bucket itself is not considered your means of insulation. Your means of insulation are your rubber gloves, or if you're using hot sticks. On the right-hand side, you see a couple guys in a substation. They're suspended in a conductive bucket, but you see they have isolated the leads back, and they've also grounded these leads. But one of the things that's missing that you'll see here, and this was a photograph from an audit that we did, they're not bonded in, but that's not our topic for today. We talk about that later. Now, isolation is opening a breaker. If we open switches on either side of the bus that we're working on, we have physically separated that bus away from the from the source of feed. And if we have control over those switches, we consider that isolation. If there's a possibility that that circuit could become energized, that's when we ground, or we work it as if it is energized, even though it is isolated by switches. There's a very big gray line between isolation and insulation, because you may have both work techniques being used at the same time wherever you're at. The question I get frequently from clients is opening a dropout switch isolation? Yes, it is. Now, you may have a lot of considerations about isolation, and because, well, what happens if the switch bounces closed? And I have a good, he's retired now, good work buddy of mine when I was a lineman, Ed Pipio, who was sitting on the other end of cables from a three-phase pothead, and a bulldozer twanged the down guy and flipped the switches closed on him while he had the cables open in his hands, and put him in the hospital for a while, and very uncomfortable. So, but the actual distance, what we're going to be talking about MAD in a minute, and you know that on a distribution circuit, the MAD distance is about 2 feet 2 inches. Somewhere around there, or 3 feet, depending on what your utility standards are. And so we have people say, well, this isn't MAD because that distance isn't 3 feet. But that's not the same thing. In this case, this is a fixed device. If you leave take the barrel out. And we have standards in the industry that set up the air gap necessary to be considered isolation across the switch. And in those standards, which we're not going to take the time to get in there and discuss that, but in those standards, you'll find distances of isolation that are only 6, 7, 8 inches, and that is well within the gap that's on that switch. And you're going to see why that is in a minute, because we'll be talking about something called MAID, the minimum air insulating distance, which is one of the components of MAD. And when you understand that, it helps you to understand what it is that we're supposed to be doing. We're also going to be talking about the nature of cover up and how cover up is supposed to be done. And that's going to be for distribution. And we're going to get into transmission. And in particular, I had a well-respected colleague sent me a note and asked, are you going to discuss TOV? And usually we discuss it on a very low level, but the more and more that I talk to clients, I have a lot of people that disregard TOV, and that can be a deadly mistake. So I've decided to add a little bit more information about this phenomenon, transient overvoltage, and I'm going to talk a little bit how it happens and how it can be controlled, and how dangerous and unexpected it is on a phenomenon that occurs on a circuit. Now, here's a table that I told you about, 441.1. That's out of the standard IEEE C37. And this is those open gaps that's required in order to create isolation. And you see here in a substation, it's 7 inches, and out on the line, it's 5 inches. And that's well within the gap that's created by an open dropout switch. So that is considered isolation. Now, you see in the bottom, insulation is to work energized with barriers to prevent contact. Now, when I show this picture in my regular presentations with utilities, right away I get murmur and giggles because people look at it and say, oh, this is terrible. Well, let me tell you something that I've been doing for the last 20 years. I've been investigating fatalities. And we have 2 major conditions for fatalities. And one of them is fatalities that are caused by induction on grounded systems. And that's probably our number one. The other one is contact fatalities. And in every one of the contact fatalities, enough cover was not used. And what you're looking at here is a proper cover-up job. And of course, this is a complicated one because this one has 2 feeders on a junction pole. It looks like there's a buck arm that's over on the other side, up there too. But this is what cover-up looks like in a transfer of 3 feeders and with overbuild, underbuild. And most people would look at this and say, this is too much. And I get aggravated with safety people that I counsel when I hear them. And I had a lot of them that worked for me that said the same thing over the last 30 years. They're saying, well, we don't want you to build a Christmas tree. Yeah, we do. We want you to build a Christmas tree, because if you don't do it, and you don't do it right, it will catch up with you at some time. And I hear people all the time say, well, we've always done it this way and it's never been a problem. And I, in my head, add up, yeah, right up until the day that it killed your lineman. So what happens is we get into a mode of drift of risk assessment, where we work for so many times and so many years and so many jobs that we start to take shortcuts and don't even realize that we are, because they worked fine last time, but they may not work right this time. This is typical of the kind of isolation errors that we make because we don't thoroughly think through what we're doing. And I'm going to try to point out a couple of things here that are missing, and I put arrows on some of the points that you need to be concerned about. Now, they've done a pretty good job of covering up the primary over on this side, but they haven't done much work about the secondary. Now, that's a little bit of that drift that I was talking about, because as linemen, we get up into this 13, 15, and 23, and especially if we get into transmission work, and we start to really lose respect for what happens on the front of a low voltage transformer. The fire here and the current here kills you just as dead as primary, and the fire sometimes is even bigger than that. So they've done a lot of cover up, and this was in the middle of a preparation for a transfer that was being done that I took off of the job site. And you can see how much cover wasn't done. Now, the response for the crew was, well, we're going to have to move all that stuff in just a minute. Yeah, you are, but you still need to cover that up, because when you get into close tolerances like this, what we find, and when I say when we find it, we're talking about the investigations that we do. What we find is that the guy working on this bus over here forgets and leans back in the bucket and sticks his back up against this transformer. So So if we take the time to do cover up, and I encourage you to give your linemen that time and to take the time to do proper cover up for the work environment that you're in. And I want to tell you one way you can know that the cover up is not enough. If you've got a man in a bucket and he's up there moving back and forth and dragging rubber with him, it's not enough. And I'm going to show you a graphic in a little while that actually shows you how these mad distances are determined when you've got a man gloving on the line. So now this one is a little bit different. This one's a pretty good cover up for the work that was being done, and there's actually room to put a bucket in between these phases inside of this corner. But the one thing that's missing here is that people didn't think about is the trees. These trees are grounded surfaces. These trees are grounded pathways. And when you put a man up in a work environment like this, where he can get his back up against the trees, he is actually grounding himself in an energized work environment. So when we talk about MAD and we talk about cover up, we stand back and we look at the work environment and we identify these risks. And if we need to, we get in there with a saw and we trim trees out and we create working clearance so that we can get work in there safely. And by the way, it's kind of like moving out on a ladder on transmission. If you've got your hands on this conductor out here, then you have a mad distance between yourself and those trees that you need to consider. And that's how you determine how far back that you need to trim those trees. Now, on this category B device, this also makes a difference on our MAD and how we cover and what we do. And I've got a lot of linemen who make the mistake of thinking that this boom is what creates your isolation. Now, it's true that we test this boom. But this boom is not considered your isolation. Your isolation, your primary means of isolation are your rubber gloves and the hot sticks that you use. In a category A bucket, a category A, this boom is your isolation, and it creates your isolation of your bucket in the air so that you can make energized contact, with that circuit. But this is also a boom that gets a lot of very, very good treatment. Now, there's a good reason why category B booms aren't counted. And back in the 60s and 70s, when we started gloving, we paid a lot of attention to the quality of the boom. And we used to wash our booms almost every day, or at least twice a week. And we would wax them and keep them clean, and we would test them routinely. You'd be surprised how many booms get tested and fail their first test until the technician doing the testing goes out there and fixes this boom. Now, you also have this bottom section here, which is known as the chassis isolation. The idea is to put isolation in between this metal portion because this is the one that always gets stuck in a feeder somewhere. And without this isolation section right here, this truck becomes energized. So these are also other considerations we have for I and I. And if this boom is properly maintained, it's going to keep usually the leakage standard is less than 80 microamps on the average for the boom, keeping it very low, much lower than the electrocution hazard for the worker that's in the basket. But again, category A, this is considered isolation. Category B, this is simply considered a secondary form of isolation because your bucket is what's first. Now, and this is what we're talking about in category A. We make contact with the phase, we energize the basket, and that basket is isolated from the ground path by the quality of the liner that's in the boom. Now, we have another means of primary insulation that we use when we can't very well glove and we don't know how to stick. And we end up putting platforms up there. And we used to call these diving boards when I had to work on them. Not one of my favorite ways of performing work. But here's some pictures that I got in Arizona of linemen. And I want to show you one of the problems with this kind of isolation in MAD. So the first thing you see is they're getting ready to transfer from the old pole to the new pole. And it's also almost in reach, from where they're at. And you see right in front of him, he's got a jumper that's coming down to the phase. And what he's done is put a rubber hose over that. Well, the initial problem with that is that in isolation, insulation, and MAD, this rubber hose cannot be used in compression. So if he has to lean over and get against this while he's lifting this conductor, which he did, and we stopped him, which he did, he is now violating the integrity of that piece of line hose, and he's actually ends up then being in violation of MAD and setting up a risk. But there's another thing that happens when it comes to gloving MAD off of platforms, and you look at the kind of platform that's being used here. For a long time, we differentiated between the types of platforms as being a gloving platform or being a work platform. This gloving platform built by Chance is isolated by two insulated or isolating sticks sections that you see right here. But if you look at this one doesn't include that section. And the other thing that happens is, look, this guy he's gloving. He's got sleeves. That's great. He's got rubber gloves. That's great. He's tied down. That's great. But look where he's standing. He has inched his way in order to do the work, and he now has his foot on the clamp for the pole. Now, I didn't scream at him and yell at him when I saw this. I said, hey, mind your feet. And he looked up and he almost passed out when he realized, because now it is legal to glove up to 8 kV off of a pole, but nobody in our industry does that. And essentially, he was doing the same thing. But drift, he lost awareness of his work environment. So he's now in violation of insulation, isolation, and technically he's in violation of MAD too, because he should not be, by their work rules, he should not be anywhere close to that energized, uncovered conductor, considering where his feet are. So something to watch out for. If you've got linemen who are going to be working off of these boards, you need to do a lot of training at the ground level as they move on and off and back and forth and work around these boards, so that they recognize the hazards that are created by working in that environment. So, is this insulation, isolation, or both? This is both. Now, we are using insulation, the insulated sticks, in order to move the conductors, but we're also using the sticks to create isolation, for the worker. The issues that come in here are how we rig and where the linemen are going to be on the structure. When you get into the lower voltages like 69 and 115, it's possible for a lineman to be inside of the pole and be within the MAD of the conductor. Now, there's a very real risk there when we get into high voltage conductors associated with TOV. And we're going to discuss that at length in a minute, about what TOV is and why we have to be concerned about it. But these guys have this laid out well. They're positioned well on the pole, and this is actually a pretty good one. Now, we can't insulate this at all, even up to 69. Well, 69 we can, 115 we can't. But above 72 kV, there is no insulation in the industry that we can put out on conductors. So this one has to be isolation and air gap that provides the protection for the worker. So this is what insulation looks like when we're moving conductors. And I want to point out a couple of things. And this is the insulation of the pole, or isolation, insulating with rubber blankets, and the insulation of the arm. Now, you can also use pole plastics here, and you're allowed to cut pole plastics in order to be able to fit inside of these gaps. And we also have arm plastics that are in place. But any place that we're going to move a phase, if that phase can come in contact with a grounded surface, then MAD matters. Once I untie this phase and I pick it up, MAD, minimum approach distance, doesn't just apply to the worker. It also applies to the grounded surfaces within that work area. And here's why. Under normal conditions, when this conductor is tied down, then the only thing we worry about is the air gap to prevent flashover. But once we're moving this phase, now we have a buffer that has to be added because of inadvertent movement that applies to conductor just as well as it applies to workers. So that's the reason why we're expected to cover this arm when we're getting ready to move these phases. And I know what a lot of people are thinking, oh, 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 oh. So here's what you should be doing. When you're thinking that this is a little bit too much, or you're thinking that I've never done it this way, or this isn't necessary, you're probably guilty of breaking the rules. So I don't want to be too hard on you that way, but I want to help you to adjust your thinking to recognize that this is how people get killed when we don't do this right. Now, here's a photograph that comes from Danny Rains, and maybe you may know him. He and I have been good friends for many years, and Southern Company, which was Georgia Power, when he worked there, did a significant amount of work, research, and publishing of material for their crews on cover up. And this is one of the pictures they had that said this is an example of good cover up. Not covered where he's gloving because he's making his Mac connection right there, but they're wrong. And the reason
Hey,
is, say that?
hey Jim, I got
Yeah.
a quick question.
All right, go ahead.
Uh, Tape on the blankets.
Yeah, okay. There's nothing wrong with doing that in order to accomplish a cover up. But the problem with tape is it leaves a sticky surface that can be contaminated and it makes it hard to clean. So most utilities have a rule, don't use tape. They prefer that you use clamps in order to get it in there, or buttons with magnets on them or something like that. If you do use tape, when you take that blanket off, that blanket ought to go in for cleaning using the cleansers, the blanket cleaners that are available from manufacturers, because that tape will gather contaminants on it and can make the surface of the blanket conductive, and we don't want to do that. So thanks for that question. Now, here's what I want to tell you. This looks good. For some people, it probably looks like it's extra, but it is actually not enough. And here's why. This is the exposed conductor. The end part of this hose is not considered insulating for about the first 6 inches or so, because there is a little bit of tracking that takes place on the contact portion of the hose. But here's the problem. Most linemen think that if they can't reach that from where they work, they're safe. But that's not what the rules say. The rules say that this part of the conductor, I am not working this conductor. I am working this conductor. This is the conductor that I can leave uncovered while I perform my work. This conductor is not. This conductor, the MAD, starts at the exposure and comes back this way 26 inches, which means that it looks like he's about a shoulder length away from being inside the MAD, which is a violation. Now, if we don't teach this, and if we don't teach this as a way of making our judgments about work positions and what we need to cover, then we're making a mistake. And here's what I'll tell you that we find over years and years of work. Right here, we have the structure, or the pole is right here on the edge of this picture. And what you see here is 1, 2 rubber hose. Same thing here, 1, 2 rubber hose. On the side of the pole where you're working with the bucket, it is very hard to legally be properly covered without using 3 line hose sections on the side of the pole that you work. Now, if you recognize that this is the measuring point for MAD back up to the worker, then you'll understand why 3 hoses are necessary to make that work. So MAD applies to energized uncovered conductors and de-energized uncovered ungrounded conductors, depending on what the mode is that you're working in. If you are working in absolute isolation and you've got control of the switches and your tailboard says that you're working in isolation and everybody understands that, then you can work without gloves, you can work without grounds. There are risks associated with that. You simply have to understand what those risks are. But if you're just working de-energized, not as isolated work environment, then you are required to cover or work it as if it's hot. MAD does not apply to uncovered conductors being worked in gloves, and that's the ones that you saw in that man in the picture. Now, but hidden here, and I didn't show it to you for very long because I don't want to aggravate you, but that's a lineman who was caught up in a flash. Now, a 10-year study that concluded in 2015 by EPRI said that line workers had the highest rate for severe injuries among all trades. And the most injuries were burns at 31%, electric shock at 29%, and the highest fatality rate, which was about 18 per 100,000 employee years. And they were most, and actually it says EPR, I said most often contact with electric current. But I'm going to tell you this, these burns 31 and 29%, and here you're talking about more than a quarter of the percent of the workforce in this 100,000 employee years. Every one of these were created by a disregard of MAD and cover up requirements. So that's an important number. Now we've gotten better, and that's a good thing. Unfortunately, we've offset that with exposure to induction hazards, because as investigators, as third party investigators, and also as legal advisors in electric cases or utility cases against OSHA, what we can tell you is that it seems that we're moving away from direct contact, but we're getting more and more injuries because of induction injuries on grounded circuits. But that doesn't eliminate the risk that's out there for improper cover up. So I'm encouraging you in the hardest way to recognize that there are risks. That's another lineman who got into a bus. There were a total of 872 thermal burn electric shock injuries from 95 to 2004. Now, it takes a while for this data to catch up with us, and that's the reason why. And you see in the rest of this picture here, you might want to take a picture of the phone if you want some of these numbers, but this came out of some EPRS study information that's out there about the nature of injuries inside. I don't want to spend a lot of time here because I want to get to some of the important stuff. Okay, so in 2014, you might remember, if you were a trade craft person out there and weren't one of the safety people that were working on this, you might remember that your employer around 2015, 16, 17 came out with a whole new set of MAD requirements, and that's because of a 2014 surprise that OSHA threw on us when they revised the standards that directly relate to our industry. Now, what happened was OSHA had put out a notice of rulemaking that they were going to update the standards, and they put out a look at what it was that they were going to do. And then in the interim time, before they actually published the final rule, OSHA, or at least the guy who was working on this, and I know him, I've had some talks with him about this, he became aware of some European studies and some work that was doing about TOVs, which we're going to talk about in a minute. And he became concerned about the issue of TOVs, and he big time jacked up the MAD distances for conductors, and they published it as a final rule, which meant it became law. And when he did that, the industry went berserk, and the industry sued OSHA over the new rules, and they came to some conclusions that resulted in the MADs that we use now. So even the distribution voltages had very high MAD that were calculated against TOVs, but it turns out that TOV isn't a big deal in distribution, but it still applies to transmission. All the way up through the mid 80s and all the years that I was working, we always used 2 feet for 4 and 15 kV, and most utilities used the 2-foot rule, and I worked there just fine in the same thing. But now we're all the way up to more than 2 feet, and sometimes out to 3 feet. Now, the other part is that.
Hey, Jim.
Go ahead.
Sorry, you got a question here. What does Jim mean by employee years?
Oh, this is a calculation that we use to create averages or percentages against the number of years that employees work. So if you had 100 employees that worked for 10 years, that's 10 times 100, or 1,000 employee years. So they use employee years as the standard in order to calculate percentages. So when you saw that page where we had percentages of injuries, like 32% electrical contacts, that 32% of electrical contact was per 1,000 employee years on the job. So it's a baseline in which to measure against in order to calculate risk and percentages. Okay. All right. If you can't quantify it, you have to assume that it's hazardous. We're talking about here about induction. Now, we have an issue with induction in that uh, we have a lot of low-level induction, and linemen forever have been coming up to de-energized distribution next to a transmission circuit or to a transmission circuit, and they come up and they bump against it and they get a shock. And they go, ooh, that's bad static on here today. It's not static. This is induction. It's the same thing that makes a transformer work, and it will kill you. Static won't kill you unless it's lightning, but AC voltage will, and that's what induction is. And these de-energized circuits that are subject to induction are also subject to MAD. And we have an OSHA rule that says, and this became effective in 2017, is that the employer must calculate the level of induction. And if you can't calculate it, which this is a graduate level calculation, you can't do it on the crew or on the job. But if you can't calculate the voltage level that's going to be on the lines, you have to assume that it's hazardous. And you do need to do that. There are two forms of induction that we detail and we study uh, in our grounding class that we're not going to take the time to do here, but there are numerous instances where induced voltages will kill you if you don't respect it. You must treat these de-energized circuits where they're subject to induction as energized, and MAD does apply until you have properly grounded and bonded the worker in where induction is a risk. Now, the MAD rules that we have now that we work by, the MAD rules are regulated both by the two OSHA standards, which are the 1910 standards for maintenance and operations, the 1926 standards for construction, the National Electrical Safety Code, and in particular, IEEE 516, which is Guide for Maintenance Methods and Energized Lines. Now, here's what's important. OSHA standards tell us what we must accomplish, but they don't tell us how to do it. Your manual on how to do it, the recommendations on best practices are these consensus standards. So if you are a safety person who is developing rules for operation of your system, you want to get copies of these consensus standards that apply, read them, and use them to judge or audit your procedures and to help you to understand what you must do to keep your workers safe and to apply. That's the value of these consensus standards, and I can't emphasize that enough. Um, we have a general duty responsibility to keep ourselves safe. So if you don't know what it is that you need to do, find the resources and make sure that you have a reason for doing what you do, and also that you understand the limitations of the cover up and the air gaps that you have. So all employees, and of course we have the training requirements that comes from the OSHA standards that tells that we are required to have demonstrated proficiency in the work practices that are involved with cover up. So if you are a manager at your utility, you need to recognize that not only do you need to train, but you need to observe work and you need to make corrections if MAD is not being properly applied. So let's look at some definitions here. And I mentioned this earlier, so I want to tell you what this is. MAID, M-A-I-D, it's the electrical component of MAD. This is the air distance necessary to prevent flashover to the nearest potential that would be in or close to the conductor. Now, if you're a gloving lineman, you know that you can take a pair of clines and you can move it toward the phase. And when you get about 3/4 of an inch away or 9/16 inch away, the phase will arc over to your clines. That's a lot of fun. I used to chase and electrocute spiders that way in pole tops, but that's another story. That is associated with MAID. If I have a fastened conductor on a pole top, and I bring a ground into it, when I get almost to that MAID, it's going to go flash to ground. And just like a man being up next to that, and especially a grounded man, this conductor will arc over, and that's the MAID distance. MAD is a combination of MADE and an inadvertent movement factor. This inadvertent movement factor is a guy standing in the bucket and turning around in circles to get his safety unwrapped around his lower body. And if you've been in a bucket, you know what I'm talking about. So you'll be up there in between your phases, and you know that you've got a phase on the right hand side, and you try to turn to your left, and your safety has got you bound up. And so you do a little spin around on the inside. And when you do that, you lose awareness of where your elbow is or your body, your shoulder is, and you find yourself brushing up against your cover. This is that inadvertent movement distance that's in there. And in distribution work up to 72 kV, that inadvertent movement is 2 feet added to the MADE, and that's what creates your MAD in distribution. So here's an example, of this inadvertent movement factor from Table 6 in the OSHA standard, and you'll also find this in the IEEE standards. And you see right here, 750 volts to 72 kV, 2 feet. Above 72 to 800 kV, it's 1 foot. And usually people say, well, higher voltage, why is it a smaller distance? Well, the reason it's a smaller distance is because we have the benefit of spacing of conductors and airspace across insulators that make our inadvertent movement less of a hazard as compared to distribution, where we'll be up between the phases and up around the cross arm, and everything is already only 12, 14, 18 inches apart. So that's the reason why we add that distance in MAD. So you see here then that in this table that we created here for the presentation, at 15 kV, the MADE is 2.28 inches. The inadvertent movement is 2 feet, and that's where you get the 24 inches, 25, 26, 27 inches. We go up to the next size. At 36 kV, the MADE is 9.5 inches. 2 feet 9 or 2 feet 10 inches. At 69 kV, the MADE is 1 foot 7. Something's wrong about that. I have to go back to that later. 1 foot 8 inches, or it may be 7 inches, 0.8. And then that gives you a MAD of 3 feet 7.8 inches. Yeah, I guess that is. I got to pay attention to this better. MTID. Not going to spend a lot of time on this because we actually use MAD for the most part. But if you're working in bare hand work, MTID is a consideration depending on how you might be using ladders. But that's a minimum tool insulation distance, or the minimum length of insulation required from the conducting part live end of an insulated tool to the closest point at ground potential. So this would be a ladder fastened to the structure that the lineman moves out on, and he has to get at least MTID or MAD away from the structure before he enters MAD coming in the other direction. We're not going to spend any time on transmission, like that, but just to give you an idea where MTID might be used. Now, this is the same. Minimum approach is the same as MTID, but includes tools subject to inadvertent movement. So that's the minimum approach for tools as opposed to minimum insulating distance. There also is one for helicopters, and this comes from studies over the years that have been done that finds out that circuits will arc over to a helicopter. And so there is a MHAD, or minimum helicopter approach. And again, we're not going to spend any time on that today. Okay, now back to definitions. TOV, let's talk about this. Do not underestimate this. Transient overvoltage is a surge that exceeds the maximum operating line to ground voltage. TOV is not a big concern in distribution, partly because it doesn't occur very often, but we also have tons of surge arresters out on a distribution circuit that prevents this TOV rise from becoming a problem for us. The other thing is that we typically in distribution are working phase to ground at 8 kV, and we're using 30 or 40 kV hose or blankets that produce a considerably higher insulation value if we properly cover up. You'll hear me mention PPAG in a minute, and we get to the end of TOV, I'll explain what that is. But this is an engineered gap that's designed with fixed electrodes on the modern equipment that's used to shunt an overvoltage away from the workers who are working energized circuit in the case of a TOV. Now, we also have to clearly understand how we calculate MAD based on either line to ground voltage or phase to phase voltage. Now, we have a lot of people that misunderstand this, so I'm just going to simply give you a definition and a graphic that comes from OSHA. Now, what OSHA says is we have the MAID, which is represented by the small circle in the middle. This is the conductor, and we have the MAD, which represents the inadvertent movement. Same on B phase. So let's say this is A phase on the right, B phase on the left. If we have a conductive object in our work, so I'm over here and I've got a conductive object, and if that conductive object is long enough to get into the MAID of both conductors, then your exposure is phase to phase. And when you use the tables, you must use the phase to phase calculation. But if you in distribution have effectively covered up these conductors, then your exposure is only this phase, so your exposure is phase to ground. And that's what shortens up your MAD distances. So this is the way that OSHA and consensus standards agree to determine what multi-phase exposure is. So if you're covering B and C phase, working on A, then you only have a phase to ground exposure. And that's also determined for the rating of your gloves and the rating of the cover up that you're using in that work environment. In the early 70s, I mentioned this earlier, I'm not going to spend much time on this, but this is again about 516, the IEEE Guide for Maintenance that was created by the ESMO group of IEEE. And this is a very high value to you. Now, in this edition of the guide, tables were calculated with new calculations, including TOV and minimum air insulation distance. So let's talk about TOV. You remember I told you that the industry sued OSHA when they first came out with the new TOV standards. The industry was successful in getting some reasonable numbers that are out. Now, in distribution, we cover up. But like I said, we cannot cover up when it comes to transmission. So we get stuck with having to rely very heavily on airspace. And if you look at these guys, this again is a mistake. Now they covered up as they went in, but this is one of those environments where they're moving hose back and forth because these guys working on this conductor are now within the MAD of the conductor that's behind them. That's a violation of the standard. Now we don't care as much that it's a violation of the standard, but the standard is there to keep you from getting killed. So they're not following the rules that are there to protect them, and we need to make sure that they do. Let me move along here because I'm going to run out of time, and I don't want to get too far away. But look at this rule from here, L52, related to what we just looked at. When an employee performs work near energized parts at more than 600 volts, but not more than 72, and is not wearing rubber insulating gloves, being protected by insulating equipment covering energized parts, performing work using live line tools, the employer shall work from a position where he or she cannot reach into the minimum approach distance established by the employer. And so this is what that would look like. If I'm in a bucket and I'm working on an energized in an energized environment, and maybe I'm hanging a transformer on this pole coming up from this boom, then MAD starts here. This is my reach, and maybe whatever tools I'm working with or jumpers I'm working with might be this extended reach. But look what happens when I put a circle there that represents the sphere or the plane of the energized exposure, the MAD. And you can see here that this lineman is well within reach of the MAD. And this is where I told you before that these three line hose appropriately apply to make sure that we that we properly cover. Now, this air, remember this MAID that we've been talking about, this minimum air gap, is affected by the temperature of the air, barometric pressure, altitude, humidity, impurities in the air. I had a customer when I was at one of the utilities, a manager that constantly flashed over. And it turned out that there was a fertilizer plant nearby that was working with iron. And as they were working, the dust would get in the air, would cover the equipment, and would create flashovers because of airborne impurities that were in the air. And then dimension and shape of electrodes. And let me explain that, because now we're moving into transmission exposure. Now, these guys aren't working energized, but the picture is a great way to start a graphic to help you understand about electrodes in the air around the conductor. Now, the yellow teardrop that you see here is there to mimic what happens along a string of insulators. The voltage collapses up the string. Now, this field of voltage, this field collapses because of the insulating resistances along the length of this string. And as we move up, the voltage collapses, and the voltage collapses uniformly. And that's created by the engineered design that creates a uniform collapse. But if I stick a conductive object like a lineman inside of that uniform collapse, I disturb that field and I create a movement or a swelling of the field that can push the voltage up the insulators at a higher rate. So if I position my bucket and myself next to a string and I get above that conductor closer to the structure, the bucket and the men in the bucket can create a change in the field, and it can change the voltage collapse over the length of the insulator, creating that can create a flashover. Now, you may have been working up there for many, many years and never heard anything like that. But now we have high-speed switching, and we have this TOV that we're going to talk about in a minute. And when we get a TOV that might occur on a circuit while we're in that space, then we're due for a flashover, and we're going to be in the middle of that. Now, we already talked about aid, so let me move ahead, because I do want to get to this TOV. So here's a definition. It's a voltage surge that exceeds maximum operating line to ground voltage. A PPAG is a portable air gap. You're going to hear me talk about this, again, and I'll explain how that works, in a couple of minutes. So what is TOV? Okay, now first of all, disregard the grounds. I use this picture here because it kind of shows where TOV catches you off guard. You may find yourself very, very comfortable working in this position on an energized circuit. I hope not, because this is a bad place to be. But these guys are actually, what they're doing is they are replacing bad brackets on these arms, and that's why they're where they're at. They are not there in an energized location. Now, here's what the TOV is. Transient overvoltage has several sources and varying magnitudes. They're caused by tripping power transformers, switching open capacitors, and circuit breaker operation are the most common causes, and I'll explain why that is in just a minute. In a TOV, frequencies have been measured in the lab in these TOVs at 100 hertz to 10,000 hertz range. Now, we work 60 hertz. Our whole system, including our insulation system, is designed to withstand voltages at 60 hertz. When these TOVs occur, frequencies of voltage on the circuit can up to be to 10 kilohertz range, which can easily flash over an insulator that would not flash over at 60 hertz. A TOV on a transmission circuit can rise to 300% of normal voltage. And what that means is that the 230 circuit that you were working on is now 690, or the 500 circuit you were working on is now 1500 kV during this TOV event. So this is a serious thing that happens. Up until 2008, there wasn't much literature on TOVs, and so that's the reason why you in the field have probably never heard about it or don't understand it. And because you've never seen it happen, I will tell you that the only TOV I have ever seen was up on the ridge in Arizona under a 345 circuit. Now, the circuit came over the edge of a cliff that went down the line, and we were standing in the right of way, and we heard what sounded like a jet coming up the circuit. And when it went over, we were standing on the ground, and it lifted our hair just like we were doing bare hand work. And it was a TOV from a circuit operation that occurred while we were standing in the right of way. And if we had been simply in the MAD or outside of the MAD, then that 345 circuit may have been somewhere around 800,000 volts. So they do occur, and they can occur while you're working. And the problem is you don't know when. Now, here's what causes it. High speed under gas or vacuum, the breaker contacts open, but when they open, they create a voltage gradient across the breaker. And here's one of the things that you may not also realize, and this is just one of the technical aspects. When a high-speed circuit breaker opens, the arc or the current doesn't actually interrupt until it hits zero in the waveform. And each one of the phases hits zero at a different time. So technically, at the speed of light, one phase will open before the other two do. And we end up with a gradient being created, a voltage gradient across the gap. And depending on the type of load, which is fault current or reactive load or something like that, depending on the type of load, depends on the gradient that's created. And if the voltage in the gradient can overload the air gap between the switch, then a momentary restrike occurs. And when that restrike occurs, what happens is that when the switch is opened on, let's say, on both sides of a transmission circuit, a voltage was trapped instantaneously on the circuit, and then a second restrike was slammed into that circuit at the same time. So that's a basic estimate of how the TOV occurs. Now remember, this is all occurring at the speed of light and the speed of time, and it only takes that fraction of a second for the flashover to occur and toast you well if you're inside of that space. So the best way to prevent this is I'll show you a study in a minute that's recommended by the IEEE for some of the things that your utility can do or should be doing if you're working on energized transmission circuits. So the best way to prevent this is if you have adjunct apparatus like capacitor banks or reactor banks that are on the line, open them, take them offline while you're doing your work. This ensures that something is not going to cause them to inadvertently or unexpectedly open because of a relay scheme that occurs, someplace, and that limits the number or the opportunities for unexpected openings of the circuit. The other is to employ arresters and shunt a circuit, a structure away from where you're working. We'll talk about that in a minute. Now, the arresters, what the arresters can do is that if you have a TOV on the circuit, arresters, of course, can clip the voltage and send it to ground and eliminate the voltage or limit the voltage rise that occurs on the circuit. Now, over the past 10 years, I have been with some crews where they have been testing high voltage arresters and putting them on the line on transmission circuits to see how effective they are. So, but the problem is that these are usually only in the substations, not out on the circuit. And if the arrestor is not in the opportune position to be exposed to the TOV, then it may not be very effective. It actually needs to be between the switch and the circuit in order for it to be effective. So there's research that's being done now and being developed. Now, when we talk about the PPAG, the portable air gap, now you know that if you've been building transmission for a while, you know that you have some wood strain, insulating strain conductor on down guys. And you also remember that a number of them were built with an electrode or a piece of conductor that sticks up at both ends. And that's an air gap. And the idea is that if there is a high voltage, before it would burn through the wood, it would flash over the air gap. Now, the problem with air gaps is unlike arresters, the air gaps will have a 60 hertz follow, which means that you may have a high voltage, high frequency flashover on the air gap, but it's going to arc over and it's going to arc to ground and it's going to trip the circuit. So that makes engineers and operators very, very opposed to the use of air gaps. Now, back in the 70s and early 80s, when I was a transmission lineman, we were using air gaps. They only protect the worker. They raise the possibility of an inadvertent lockout somewhat, and that makes utilities afraid of them. But utilities have to understand their responsibility in controlling these TOVs and protecting the worker out on the line, and a lot of them don't do a very good at that. Now, this is how a TOV works, or how an air gap or a PPAG works. We don't put the PPAG on the pole that we're working on, but I'm going to show you a graphic here to show you how it works. We have a normal collapse of voltage up the insulator, and then we have some additional insulators in the string to provide force surges and to provide a measure of buffer over that string. Now, the possibility is that you may be on the outside of the normal collapse of voltage, but a TOV occurs and this whole string can flash over. So what we do is a structural way we install the PPAG. The PPAG, the portable air gap, what it does is eliminates the buffer of this string by putting a ground just outside the normal voltage collapse for the insulator string. So now if a surge comes by and overloads this string, this ground will catch that surge and it will go to ground and lock the circuit out, and it will do it before it can get to the crew that's a span away. So the problem with with a PPAG is that it can cause an inadvertent lockout, but it's going to be totally resistive, and it's unlikely to actually create a TOV if it does trip the circuit, but it's obvious that it could occur. So we also are in development, engineering or companies are working on developing portable surge arresters, which would be preferable to a PPAG. So what we would do is we would go a structure away on either side of our work location, and we would install arresters, portable arresters in on the circuit to reduce that. Here's the paper I was talking about. If you're in the safety department or policy making, that you need to see the ESMO subcommittee. The name of the paper is Practical Approaches to Reducing Transient Overvoltage Factors in live work. So we're getting more and more in the industry, and we have numbers of our clients that are coming to us and asking for, and we're doing a lot of bare hand training that we haven't done in the past, because more and more utilities are unable to conveniently take circuits off the line for some normal or low level maintenance. And so we've got more of them that are wanting to do live line maintenance. And if we're doing that, TOVs are an issue. This is a fixed PPAG. This is the conventional or the contemporary type of PPAG. And what you see here is the arcing horns. You fix it to the structure at the grounded end. You fix to the conductor at the hot end. The probe, the horn is hot. The air gap will not flash over unless the voltage reaches a maximum value, and it will flash over. And on this end, there also is a lead. This is where your ground connection takes place. So it looks like this. Now, of course, you see them making the ground connection now that the PPAG is in place. You see that air gap that's created here at this location. The other thing that this does is, in the old days, we put the PPAG on the insulator string. And if it did flash over, it would damage the string and we would have to replace the string. This eliminates that possibility of damaging the string because the flash happens in the air between the probes, that occur between the two. So you have to make sure this is good, clean, well waxed and doing its job before you put it up there. You can't move these on these because they are fixed for voltage based on the MAID and a buffer from the consensus standards, in the industry. So the issue for contractors, if you're a contractor out there, your customer is supposed to give you, remember, information in the information transfer. And if you're doing transmission work, They don't have to tell you what their MAD is, but they are obligated to give you the information that you need so that you can calculate MAD for the work that you're doing. And what happens is then you go back to the calculations, or you go back to the tables that have the TOV multiplier in that table. They tell you what their calculated TOV is, and then you go and use it. So use the tables using that TOV. So the point is that I do not want you to underestimate the hazard when it comes to MAD, insulate, and isolate. And I want you to understand that this TOV is a real live problem. And you need to be aware and not to disregard it, because if you're doing hotline work in transmission, your normal MAD distances may not protect you if you're not calculating TOV. So I hope that I would love to have been able to go through this whole presentation. There's a lot more information that's out there that's available. I do want to give you this my contact information. There's my email address, Jim at ISPC Online, or you can text me at 480-708-2999. I sit here in Louisiana waiting to hear from you if you have questions about your compliance issues, or more questions about issues with insulation, isolation, and MAD. We're here to help, so feel free to give me a call. So with that, we've taken the hour that we promised you, and I'm going to turn it back over to Ryan, and he can wrap things up. I look forward to hearing from you. Thanks.
Hey, Jim, do you have a second to answer just a couple questions?
Yes, sir. Go right ahead.
Okay. From Robert, it says, does the wearing of rubber sleeves buy me any leeway from the end of the line hose cover when it comes to adding hose because of a 2-foot 2-inch possible reach of the hand or
Yeah.
tool?
And that's an appropriate question in this way. See, here's the problem. Outside of the hose, you're not working there. You're working inside of the hose in the gap or in the area that you're in. So you have to think about this from the technical application viewpoint. You're only allowed to expose yourself when you're wearing rubber gloves to the work that you're actually doing. That conductor at the end of the hose is not your work area. So that conductor at the end of the hose is where you measure your MAD from. And, that's if you can reach into that, or the tools that you're working in, you can be in violation of MAD. So, the thing is, it's not about wearing gloves. It's about that's the part of the conductor that you're not working on. The gloves and sleeves apply to the conductor that you're working on. The outside of the hose is not the conductor that you're working on. So technically, gloves and sleeves don't matter. If you can reach into that space, that's part of that inadvertent movement. And now that's talking about your back, your shoulders. That's also talking about the jumpers in your hands, or the conductive tools, or equipment that's in your hands. And that's the reason why it would not apply to the end of the hose. Great question, though. Thanks. What else you got?
Okay. One last question. Do the TOV numbers always refer to phase voltage?
Not always, because your exposure usually is only phase to ground, because you're well away from the other phase in transmission. But what you will see on the tables in OSHA is that you will see phase to ground and phase to phase. But remember the graphic that I showed you. If you are working with tools that can go into the MADE of both, then you have to consider phase to phase. But in most all applications, if we work in our conventional work methods, our only exposure is phase to ground. And if you look at the alternative table that OSHA provides for TOV, the alternative table is calculated at 3, at a T per unit of 3, which is like 3 times. And you'll find that the MAD for 500 kV at a TOV element is like 23 feet. There's no way that you could work or even climb a structure in that case. Now, we'll tell you this. The guy that wrote these tables, we were actually across from each other in a litigation. He represented OSHA, I represented a contractor, and we were just shooting the breeze. And I said, hey, what's the deal with TOV of 3, in the alternative table? And he says, well, frankly, we put it there to encourage people to actually calculate. because typically TOVs are going to be 1.5, 1.7, 1.82, somewhere around there. He says we didn't think that anybody would ever think that they were going to have to work at a TOV of 3. So it was put up there in order to compel our compliance. But the way that we work, back into the answer to your question, the way that we work, if we work single phase to ground, our TOV or our MAD calculation with TOV is phase to ground. Okay, is that it, Ryan?
That's it. Yep, that's the
Okay,
last
it's
question.
yours. You go ahead and take it away.
All right. Thank you all for attending today's free webinar. We're going to have another one in March, so be on the lookout for that. And if you can donate today, please click on the link in the chat. If not, you can also go to the ISPC website at www.ispconline.com and click on the donate button there as well. And we look forward to seeing you all again next month. Thank you.